So here's another ideal transformer problem, and this one is a little bit different because we've got two, and notice that we don't have the nice uh, localization or location of the dots that go with the tops of all the ideal transformers. But that shouldn't be a big deal. As I say, the big thing with ideal transformers as well as mutual inductances is, I think, to label them the way that the book labels them so that you can do everything like you want. Now, what this wants to know is the average power in each resistor. So it's not really a big deal, but because this is, since it is in the time domain, but since everything is resistors, the ideal transformers are lossless, right? So what's the power lost in transformers? And that's because these are ideal. 0 watts. So the only thing that's going to deliver power is the source, and the only thing that's going to absorb power are the 1.5 ohm, 50 ohm, 38 ohm, and 9 ohm resistors. So, okay, that's one thing we should sort of notice. I guess the first thing we should do is take this circuit and convert it to the time domain. And so I'm going to paste this back in here. And since we had 5 cosine 120 pi t, omega was 120 pi, which gives F, which is omega over 2 pi, is 60. So this is 60 hertz. So this is like power frequency, what's coming out of the wall in this country. So this would be 5. The phase angle is 0 degrees, so in the phasor domain this would be 5 angle 0. I believe this is actually, I don't have a book with me, but it said amps, and I don't think that this is in RMS, because this is all in resistive form here. So I think it's just 5 angle 0 amps, not amps RMS. So we should be able to just take things like I said I wanted to label these such that it's similar to the ideal transformers in the book, and so how they label it is the plus is at the dot, so I'll call this one plus to minus V1, this plus to minus V2, so the pluses go with the dots. Now for the primary side of the transformer, they have the current going into the dot, I'll call this I1. For the secondary side, for the ideal transformers, they have the current going out of the dot, so that's I2. Okay, the next transformer, I'll do V3 and V4 for this, so plus to minus I'll label that way. Plus is at the dot down at the bottom for the first, or the primary side of the second transformer I have here, and then plus to minus V4 at the secondary side of the second transformer I have there. Now, the current needs to go into the dot, I'll call that current I3 for the first one, and the current needs to go out of the dot for the second, so I4 for the second one. Now notice, okay, I should be able to see straight away that I2 goes clockwise around that loop and I3 goes counterclockwise, so I2 is minus I3. That's not really a big deal here, but I think it's better to go ahead and do it this way so that you don't mess up the signs for anything. Okay, the other thing, since we've set up the transformers like they are in the book, then we can go ahead and say, okay, well, V2 over V1 is 9 over 1, which is N2 over N1, and V4 over V3 is 4 over 1, and we can also do the opposite for the currents. I2 over I1 is 1 over 9, and I4 over I3 is 1 over 4. So that gives us basically the ideal transformer equations that we need, and so we should be good to go. Again, the big key, I think, is labeling the transformers like they need to be labeled in standard form in the book. Then you don't have to worry about any of these plus and minuses that would result from not using standard form. Okay, so the easiest way I think to go about this problem is probably to go and find out what this 9 ohm resistor looks all the way back on the input side over here at the primary side of the first transformer. That way the whole circuit will be all resistors. We can easily solve for V1 and I1, and then once we know V1 and I1, we can sort of backtrack and find V2 and I2, which will then allow us to find V3 and I3, which then will allow us to find V4 and I4, and once we have all that, we have all the information that we need for this problem. Okay, so if we have ZL is 9, remember there's no other resistance beside that in that last branch over there, so we can take the load impedance and we can say, okay, we'll convert to primary side of second transformer. So we need to know its ratio, and its ratio is 4. So the formula is Zn equals ZL over A squared, and so that would be 9 over 4 squared, so 9/16 ohms. So what that means is basically I can come over here, I can paste my circuit again, and that means I could erase over here and put at the primary side of that second transformer 9/16 ohm, because that's the input impedance. So we've replaced the rest of the circuit with that. Now notice, now I have 9/16 ohm and 38 ohm, right here. Those two are in series. The same current, I2, or we could say I3, runs through them. Doesn't really matter. And so the total resistance there is 38 plus 9/16, and we need to take that to the primary side of the first transformer. So again, this should still be just 5 angle 0. So now we've got 38 plus 9/16, and we need to divide that by the turns ratio squared, so that's 9 squared. So, and I'll call this Zn prime. So Zn prime should be right there. And so now I can draw this circuit again. and that resistance is what I'll call that Zn prime, and notice we called in our drawing this is V1. That's I1 going into the dot. That's where the dot was. Well, now everything is nice and simple. This was 5 angle 0. We can do a nice simple, call this our reference node, call this node V. We can say minus 5 angle 0 plus V over 1.5 plus V minus V1. Well, maybe I'll just do it over the whole thing, not do it in terms of V1, but I'll say V over, and I'll add those two together. So I'll have 50 plus Zn prime. Alright, and that sum those currents up, and that's equal to 0. And notice that this current I1 is equal to that V over 50 plus Zn prime. And we can also write V1, which we'll likely need to know, is I1 Zn prime. Okay, up earlier in the problem I actually talked about the current here being this 5 angle 0, and I talked about it being in peak. I actually looked at the book problem, and it does indeed appear to be in peak, because normally if the book is going to say something, they'll clearly write it as like 5 angle 0 RMS amps or something like that, and they don't put the RMS in there, so I suspect that they mean to indeed have it in peak. Okay, well, that means for us, if we want to do things in peak, remember the formula for complex power, if things are in peak form, is 1/2 the real part, well, let me say the complex power S equals 1/2 V I conjugate. And P, which is the real power, is the real part of 1/2 V I conjugate. Now, if they were in RMS, remember it's just VI conjugate, real part, or VI conjugate. Now that's if these are in RMS. This is if these are in peak. And of course that makes sense, because what are the peak and the average values in terms of their relationship between each other? You take V peak and divide it by square root of 2 to get V RMS. I peak divided by square root of 2 to get I RMS. So if you multiply VRMS times IRMS, you can see that you could also multiply V peak and I peak, divide it by 1/2, and you get the same result. So that's why you need these 1/2s in there when you're having the peak power. powers will relate between the two. So, let's see, where was I headed towards? Okay, so obviously, these two forms give you the same thing, 1/2 VI conjugate for S if the V and the I are in peak, VI conjugate if they're in RMS. Those two forms are the exact same. Okay, well, since this is in peak power over there, then one thing we need to do is really convert this 5 angle 0 to square root of 2. Or we can say that our values are in peak and calculate formulas based on that. But I generally think that, we're sort of used to using those formulas in the early chapters, like V squared over R or I squared R. And remember, that's really requiring us to be in RMS values, because if we looked at DC sources, the RMS value is the same as the DC value, and so that's how they're related to each other. Remember back in the lecture when we talked about that. So I think it's better to go ahead and convert to RMS, and in which case I would come over here and all I have to do is divide that by square root of 2, and now all my voltages that I find here and currents and voltages and whatnot, those will all be in RMS. So that makes it real easy to do. And so then once I've gotten this V1, then this V1 that is equal to I1 Zn prime, okay, well, that's great. That is in RMS. And if I want to find the power absorbed in the 1.5 ohm resistor, then the power absorbed in the 1.5 ohm is that V, because V is across here between there and my reference node, and I need to take that value. Okay, when I'm using that formula, I should use V conjugate over Z conjugate for, remember, this is I conjugate, but everything is real here. I don't have any complex numbers going on, because I just have Z's, or my impedances are all resistances, and my voltage and currents are all in phase everywhere. So this really just becomes V times V again over R. So this is just V squared over R. And so one thing that you should make sure you're aware of is this is indeed needing this V that we have here in RMS, which we did put in RMS because we went and divided the peak value by the square root of 2. I will be specific on the tests when we're looking at this about peak and RMS values. Most of the time I will actually have things in RMS, but I will try to be specific, and if you are curious, definitely ask me. Okay, so that's the power absorbed, and if we want to know, I think this problem actually asks the power generated by each resistor. I don't know why, but if we want to know the power generated by the 1.5 ohm resistor, it's equal to minus the power absorbed by the 1.5 ohm. So, okay, that's that part. And what about the 50 ohm? Well, we've got I1, and that's this value right here. It's that V that we've got divided by 50 plus Zn prime. And this is in RMS because I changed my 5 angle 0 current source into RMS by dividing by square root of 2. So all my currents and voltages are in RMS. So then once I do this, I can use the power in this 50 ohm is equal to, again, the real part of VI conjugate. I don't know that I said this here, but the real part of that. It's all real. I mean, we don't have to worry about this since V conjugate and V, all of those are real values. Z conjugate, that's just a real number, so it doesn't really matter here. But this is, if I want to change it, V to be equal to IR, then this is IR I conjugate, and I need to take the real part of it. And so this is R I conjugate, and that would be R magnitude of I squared. And I guess I should be careful that this is not VI. I should be careful that the voltage I'm talking about is the voltage now is V across this 50 ohm, and the current is I through that 50 ohm, and that current that I'm talking about in this case is this current right there, and so that is I1, and so this is I1, this is I1, this is I1, 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 so magnitude of I1 squared, and of course we're used to I1 squared R. I1 squared is the same as the magnitude of I1 squared here, since it's in a purely real number. But to be honest, I like this form right here a little bit better, even though it results in the same thing for this problem. Okay, so we've got that. Make sure you realize that this V is the voltage across that 50 ohm, and in which case that voltage right here, I probably should not have called it V, but this voltage is actually V minus V1, but I just called it V. Maybe I should call it VR right here and call this VR, and call that I1, and then all of that will make better sense there with what I've got. So okay, so we've got that. Now what I want to do is find the power in the 38 ohm and the 9/16. Well, not really the 9/16, because that's sort of a fictitious resistor that I've created by translating the secondary impedance on the second transformer back to the primary side of that second transformer. I really just want to know the power in that 38 ohm and in the 9 ohm. So I come back here, and remember, I can always use my formulas. Okay, I found V, I found I1, I found V1, because I know Zn prime, know all that stuff. So I can use my ideal transformer equations, which are up here. That is, V2 is equal to 9V1. So I'll just copy these down. And so what that tells me is that, okay, I really don't need V4 and V3 quite yet. But I do need these. So that tells me that V2 is 9V1. And notice above I've already found V1 right here using that equation, and I also have I2 is I1 over 9, and since I know I1 I can find I2, so I'll have both of those, and then I can get, since I2 is flowing through this 38 ohm resistor, I can take again the real part, and I'll call this of V38, and I'll say I38 conjugate. Well, V38 is just 38 ohms times I38, so resistance times current, times I38 conjugate. You need to take the real part of that again. Well, I38 conjugate is just 38 times the magnitude of I38 squared, and that whole thing, that, magnitude squared, again, it's just like the case up here. Magnitude squared is always a real number, so I don't even have to, the real part of this is just this. And what's I38? Well, notice I38, that should be the current going from plus to minus there, and that's the same direction as I2, so I can have this as 38 magnitude of I2 squared. Then, okay, now I could get the power in that 9/16. Again, I could use that current I2 and basically say, oh, it's I2 squared times 9/16. There's no problem with saying that. P absorbed 9/16 is equal to, it's going to end up being 9/16 magnitude of I2 squared, because that current is in series with all that. But that's not really a resistor in the original circuit. But we know, what should this power be equal to? It should be equal to the power that is absorbed. Okay, the 9/16 is translated from the 9 back to the primary side of that second transformer, so that should be the same power as the 9 ohm, because there's no power lost in that second transformer. So we could we could automatically say, oh, well, that's the power. Well, okay, if we want to back it all the way out, though, maybe we want to do that and get the current and voltage in that secondary side of the second transformer. And if we want to do that, then we need to take our formulas that we had before, which are the V4 over V3 is 4, and I4 over I3 is 1 over 4. So we need to take these two formulas and I4 over I3 is 1 over 4. Now the only other thing is, okay, we don't have V3 yet. We have V2, but we don't have V3. And notice V2 is not exactly equal to minus V3 because we've got that 38 ohm resistor there. So we actually need to use voltage divider or some other technique, but voltage divider will work. Everything is in series there, in that I2 is flowing all clockwise around there, or we could say I3 is flowing counterclockwise, because we already pointed out, that I3 is minus I2. But we could use voltage divider and say, oh, well, the total voltage there is V2, and it's spread across both the 38 ohm and the 9/16 ohm, and those two are in series, so we can use voltage divider law to get that. Okay, if we're going to do that, we can say V3 is equal to 9/16 over 9/16 plus 38. That's what voltage divider says. Take that ratio, multiply it by the total voltage, which was V2, but the only thing we have to add is, okay, notice that V3 is wanting the polarity from minus to plus, and that's not the way the standard voltage divider works, so we need to add the minus sign right there to get it. And okay, once we have that, we could also find, if we wanted to, we could find that we could write an equation that says minus V2 plus I2 times 38 plus 9/16 equals 0. So that could allow us to calculate I2, and we also can write I3 as minus I2, and then use our equations to get I4 and V4 from V3 and I3. And then once we have that, once we have V4 and I4, we can go back to this top and realize, oh, well, the current going through that 9 ohm is I4. Or the voltage across that 9 ohm is V4. Either one, we'd get the same answer if we used either one of them. And we can take, the power absorbed in that 9 ohm is equal to real part of VI conjugate, and so I'll say V9 I9 for the voltage across that 9 ohm and the current through that 9 ohm. Okay, the voltage across that is V4. I believe we have it up here. Yep. So the voltage from here to here is just V4. So this is equal to real part of V4, and I9, the current going through it, would be just V4 over 9, and I got to take the conjugate of that, and of course that is equal to the real part of V4 conjugate over 9, and so that's magnitude of V4 squared over 9. Real part of that is equal to just magnitude of V4 squared over 9. And likewise, we could have followed the same route and have gotten I4 magnitude squared times 9 as well. Any of those would work, and if we want the power generated, then it's minus the power absorbed for that 9 ohm. And notice, if you would go back and calculate, if you plug all these numbers in, you should find out that the power absorbed of that 9 ohm would be the exact same number as the power absorbed of that 9/16 ohm that was sort of a fictitious resistor that was created by translating that 9 ohm back to the input side of that second transformer. So this is a good problem, and it does show you the relationship and how ideal transformers work. One of the most common uses for these ideal transforms is impedance translation, so that you can use you can translate resistances that are smaller to maybe make them bigger on another side of the transformer, and that can hopefully maybe match the resistance for a source so that you can get maximum power transfer. You could also have the opposite, where you have a big resistance and you want to make it smaller on the other side of a transformer, so again maybe you can maximize uh, power transfer, and so forth. Okay, so that's this problem, and I just want to clarify and say one last thing about amps being, not amps, but about power in relationship to peak and RMS values. One of the biggest problems that I think you'll face is realizing that S equals VI conjugate is the formula for complex power. The real part of that is the average power, and the imaginary part of that is the reactive power. But this is the formula when V and I are in RMS. The formula for complex power when they are in peak is 1/2 VI conjugate. You must bear that in mind, and notice it's because the power in each case turns out to be the same. You don't have different values for power, but you calculate power differently to get the same power values if you are in peak value or if you are in RMS value. And of course, as I said, VRMS, to get an RMS for a sinusoid, you take the peak value and you divide it by the square root of 2. Same for a current. Now if you have a triangle wave, half of a sinusoid or a clipped off sinusoid, or a parabolic wave or anything like that, if it's not a sinusoid, you have to go through that integration procedure to find out the RMS value. So it's only really easy to calculate the RMS value for sinusoids and for DC voltages, because the DC voltage value is the same as the RMS value for the DC source. Okay, so anyways, that finishes this problem, and I will upload it now to YouTube.